The second part of this session on extracting and using space resources will be chaired by Abigail Calzada-Diaz, who you've already met during the course of the last couple of days. She's a lunar geologist working in identification and characterization of lunar resources as a research and technology associate at ESRIC. So please welcome back Abigail to the stage.
Thank you, Lisa, and welcome to this session. I'm just going to go straight to the talks because that is the important part of this event. So our first speaker, let's see if we can see the slide, is Pia Swatkowski, that she's working at Blue Horizon, and she's going to talk about 3D printing from renewable resources for future deep space exploration. Welcome, Pia.
Hello everyone, my name is Pia Swatkowski and I'm from Blue Horizon, and I'm happy that I can present to you 3D printing from renewable resources for future deep space missions as a part of extracting and using space resources. At Blue Horizon, I'm working as a project engineer. Blue Horizon is a life science startup with 7 crew members located in Betzdorf. Our core competences are bioprocess engineering, biotechnologies, Earth observation, and remote sensing. Our goal is to combine bioengineering and space technologies as a solution for extreme environments on Earth, as well as for life support systems for future deep space missions. Today's way of material use for space missions is a linear way. You see it on the left side. Materials are sent from Earth to the ISS and used as long as they last. Finally, they are disposed from the space station and burn at re-entry to the Earth's atmosphere. This approach is impossible for future deep space missions we see on the right side, like, for example, to the Mars. We need to use renewable resources for materials and the circular utilization of materials like food, water, and oxygen. At the moment, we are focusing on use cases for low-orbit missions like the ISS. Biological life support systems are such circular systems. The astronaut, for example, needs oxygen, water, and food as an input and produce carbon dioxide and organic wastes as an output. To transform this in a circular system, the waste streams, for example urine, are recycled as an input for microbes in the biological system. For enabling this, phototrophic microorganisms like Limnospira, commonly known as spirulina, are used. In a photobioreactor, the recycled urine could be used as a medium for cultivation spirulina. The microorganisms transform the carbon dioxide through photosynthesis into oxygen and biomass. Both the oxygen and the biomass can be used directly by the astronauts. On the one hand, the biomass can be used as food, or in our project, we are using to extract this biomass as a raw material for additive manufacturing. By mixing the biomass with plasticizer, we can produce a thermoplastic material for 3D printing. With further improvement, the printouts could be tailor-made for various applications like tool, boxes. Here an example. We printed it by ourselves at the proof of concept. Through adding different additives and materials, we propose to change the properties of the thermoplastic material and so of the printouts. Through the valorization of organic waste, we intend to minimize the upload demand for additive manufacturing and produce bioplastic from renewable resources in space. Our goal is to integrate the organic waste project into the Melissa cycle by ESA, shown on this slide. Melissa is the microecological life support system alternative and an example for a biological life support system. We want to use the solid organic waste from compartment 4 as a precursor for additive manufacturing and reintroduce the printed applications in the cycle as an added benefit for the crew and the space mission. I hope this provided you with the idea what we are doing. I want to thank LSA and ESA for funding and support. Thank you for your attention and feel free to contact us or you approach me directly after the session and we can discuss any questions you have. Thank you.
Thank you, Pia. I want to remind all of you that if you have any questions during this session, you can just submit your questions at any point in our platform. Or also, when the Q&A question part came up, you can also ask questions here as well. So our next speaker is Arturo Pajares. He's coming from the Flemish Institute of, let's see if we can see the presentation, from the Flemish Institute of Technological Research. Please welcome everybody, Arturo.
Okay, good morning to everybody. I am Arturo Pajares. I am coming from the Flemish Institute for Technological Research in Belgium. So I'm going to talk a bit about the work that we are doing in the institution. But so far, I've seen that many of the presentations focus on Moon, but what about if we go a bit further? So I want to start my presentation with this question. Can we use Martian regolith as a catalyst for the CO2 conversion? First, we need to define the catalyst. Catalyst is a compound or material that accelerates a reaction and make it feasible. Okay, so first, we are going to identify the resources that we can find on Mars. Carbon dioxide is the most abundant component in the Martian atmosphere, reaching a value of 95%. And also, we can find water and the Martian soil. So if we combine carbon dioxide with hydrogen, we can obtain fuels. This hydrogen can be obtained from electrolysis of water, and we have at the same time oxygen. Oxygen can be obtained also by the electrolysis of Martian soil, the Martian regolith, obtaining as well metals. Okay, but how we can make these fuels? So first, we need to trap, we need to capture the Mars atmosphere, and then to pass through a dust filter. Why? Because the atmosphere there is very thin, and the pressure is less than 1% compared to the Earth atmosphere. Okay, we capture the Mars atmosphere, and then we send to a water trap to remove the water vapor that we can find on the stream, and all the stream goes to a carbon dioxide capture process. No condensate gases can be released or can be used for another application, and the CO2 is sent to a reactor. Then it's combined with the hydrogen to produce fuels. But as I said before, hydrogen can be obtained from the electrolysis of water, producing oxygen as a subproduct. But if we want to use the Martian regolith as a catalyst, we need to take a look inside the properties of this regolith. With information from the rovers that they sent back to the Earth, NASA provided information about how it's conformed, this Martian regolith. It's basically conformed by silicates or mixed oxide. But the most interesting here, catalytically talking, is the presence of iron. Why? Because iron can be used for, or have been studied here on Earth, for different catalytic applications to produce fuels and some chemicals. In this case, we are going to focus on thermochemical reaction that basically works changing two parameters, pressure and temperature, for the production of methane and CO. Okay, so how this process can be carried out? So we mix first CO2 and hydrogen, and we send it to the reactor. The reactor is we put the catalyst into the reactor, and we obtain methane and CO. The unreacted CO2, CO, and hydrogen can be sent to another reactor that works to different conditions to obtain, in case we want, liquid fuels or alcohols. But this second reactor works at different conditions than the first one. So we are going to focus in the methane and CO production. But methane and CO production, they are produced at different conditions because of the nature of the reaction, the thermodynamic of this reaction. So a lower temperature, if we go a lower temperature, we favor the formation of methane, but a higher the CO formation. Okay, so unfortunately, we don't have real samples yet, but we are going to test simulants. There are some companies that provide some simulants. So we analyzed 3 different simulants from different generations to see the catalytic behavior in this reaction. So we test MMS1, MMS2, and GS1. MMS1 from the first generation of simulant, MMS2 the second, and MGS1 from the third generation simulant. As further we go in the generation, they show a higher fidelity. And we can see a lower temperature we don't activate, so this catalyst doesn't produce any methane. But a higher temperature, more than 350, we observe some activation. We convert the CO2. But basically, as you can see here, the CO selectivity is more than 96%. What this means with CO selectivity? From 100% of the products, 96% are CO, and the rest, 4% are methane. But also we observe here at higher temperature some deactivation. This happened because we found a structural change from iron oxide to metallic iron. Also, if we need to put our catalyst into the reactor for practical issues and to avoid some technical issues in our reactor, we successfully printed 3D. That, by the way, after the presentation, if you want, I can show you because I brought them with me in person, so you can see it. Okay, anyway, we tested. We observed a similar trend to compare to the powder form, and also the CO selectivity is very high. So basically here, we are activating the CO2 for the formation of CO. And we saw the same phenomena, the activation at higher temperature. Okay, so we went further with the MGS1 because it's the most reliable simulant so far nowadays. And we treated to 2 different temperatures, 600 Celsius and 1,000 Celsius degree under air. But these temperatures were not chosen randomly. We're choosing because at 600, the iron carbonate is transformed to iron oxide, and 1,000 magnesium sulfate is transformed to magnesium oxide. As you see in the graph, the regolith treated thermally at 600, basically we don't see any changes in the catalytic behavior, the performance. But when we treated thermally and up to 1,000, we increase dramatically the catalytic activity of this catalyst. So we can conclude here that magnesium oxide promotes the CO formation. We did another treatment. We wanted to concentrate iron as much as possible because it's our active site. So first, the MGS1, so we mill it, and then we to have a homogeneous particle size distribution, and then we sieve less than 45 microns for a better separation in the magnetic separator that works at magnetic field of 2 Tesla. And we have 2 fractions, magnetic part and non-magnetic part. So this part, we tested in our reactor, and we observed what we expected. So a higher concentration of iron, we activate more of the CO2, and we produce more carbon monoxide. The selectivity here is very high, as you see the graph. So it's more than 94% selectivity of CO. The rest is methane. But we observe here at 450 that we obtain the maximum methane selectivity, around 5.3%. That's also, we test, but I didn't show that a better separation of the magnetic part, the iron oxide, is when the simulant is treated when a lower particle size. But so far, I talked about the iron oxide and metallic iron, but actually, this is not our catalyst, actually. The iron carbide is obtained in situ by the reaction of iron oxide and CO. So this is our active side. Okay, and now what about if we separate many times this magnetic part using the magnetic separation in 4 batches in a row? Okay, so we increase the air content in the samples, and we observe a higher catalytic activity. So even we are improving now. But okay, we did different treatments, thermal treatments. We mill, we treat under different atmospheres, and this route gave us the best result for the methane formation, the highest rate. So first we took the MGS one, then we separated magnetically, and we took the magnetic part, the magnetic fraction, and then we treated under air 1000 and CO. Later, under CO at 400 Celsius. As you see the picture, the sample changed completely. The color is because of the presence of iron carbide in this sample. So as I say in the previous slides, we obtain a maximum rate of, or selectivity also, of methane at 450 Celsius. And we follow it during 20 hours. What we obtain is 30 moles of CO per kilogram of catalyst per hour, and methane 7 times lower, or around 4 moles of methane per kilogram per catalyst per hour. But maybe these numbers is not clear to talk about moles, but let's change to a better unit. So it could be liters. Liters standard condition, this 0 Celsius degree, and 1 bar of pressure, 1 air atmospheric pressure. And this is the values that we obtain, around 672 liters per kilogram per catalyst per hour, and methane around 83 liters per kilograms of catalyst per hour. So what's our future goal? Is try to improve the methane production using different treatments for this simulant. We are going to prepare the 3D printing, the structures using 3D printing technology of the best catalyst with the best catalytic results as a powder form. We're going to study different designs, shapes, and size of this 3D printed simulant that we prepare. And finally, we are going to study, we are going to make an assessment of the technical, economical of this process on Mars to see how much material and energy we will need to use. Okay, so that's all for me, and thank you so much. And this is the email if you want to contact me for any questions or for possible cooperation or contribution, scientific contribution. Thanks.
Thank you very much, Arturo. The next 2 talks are going to be online. And also, I want to remember to all the presenters also before that there are questions in the virtual platform that you still can check and you can answer to them. So our next speaker is Minkwan Kim, that he's professor at the University of Southampton. We can see you. Can you hear us?
Yeah, I can hear you.
Okay, perfect. So Minkwan Kim is going to talk about the development of all-in-one in-situ resource utilization system for future Mars exploration missions. Welcome, Minkwan.
Okay, thank you, Abigail, for introductions. So I'm the Minkwan Kim at the University of Southampton. So I'm glad to present our work at the conference. So the title of the presentation is the development of the all-in-one in-situ resource utilization system for the future Mars explorations. So this project is funded by the UK Space Agency. So next slide, please. So currently, the many of the space industry, they are planning for the human space flight for the future Mars. So yesterday we have one of the milestones from the SpaceX. Unfortunately, it was not successful, but we know the space mission with involving the human are quite different. So previous missions for the rovers, so it was the simple, but if we involve with the crew, human, we need like a different resource. Especially, we need to provide the oxygen for the breathing astronaut. So astronauts need the drinking water for maintain their life. Also, we need to bring them safely to their home. So therefore, one of the challenges we have is the getting the resource. So project we have is try to develop the resource utilization system for generating getting the clean water and having the oxygen for the breathing and generating the fuel for the returning. So currently the systems are individually different, but what we proposed using the same system can do everything at the same place. So we call that is the all-in-one, the plasma system. So idea is the Mars has basically we can harvest the carbon dioxide from the Martian atmosphere. Also from previous Mars missions, we identified there are the reasonable amount of the ice under the surface or near the polar area. However, the water in the Mars, they could be contaminated by the unknown chemical, potentially having some unknown biological contaminant. So it is not suitable to be used as the potable waters. So therefore, we try to purify this one, and also we need to have the oxygens and the carbon monoxide from the CO2. So the idea is that we're going to use the non-thermal plasma. So this non-thermal plasma is particularly useful because it has the very high electron energy. So this high electron energy we can use to excite the vibration energy of the CO2. Then we can dissociate the CO2 to the carbon monoxide and the oxygens. So this oxygen can be used for the breathing, and the carbon monoxide we can use for the returning fuel. Also, the non-thermal plasma can make the oxygen for the reactive oxygen species. These reactive oxygen species are particularly useful to purify the water by using their oxidative capabilities. The next slide, please. So our system having the two major components. One is the bubble reactors, which is mainly for the purifying the water. The system using the non-thermal plasma, as I explained, so to remove the unknown biological contaminant and the unknown chemical contaminant. So the idea is that we're gonna inject the non-thermal plasma into the microbubble. And then the reason why we inject the plasma in the form of the microbubble is to increasing its contact surface. So therefore, as you can see on the schematics on the bottom, so we place our plasma reactor on the bottom and inject into the liquid water in the form of the microbubble, and the microbubble containing the plasma will remove the chemical contaminant or unknown biological contaminant. So one of the key advantages of this system is that there no consumable is needed. All we need is the electricity and the small amount of the oxygen to make the plasma. So next slide, please. Oh, next slide, please. Yeah. So this is some of the tests we have. So top one is the before the treatment. The bottom is the after the treatment. So we use the methylene blue as the indicators. So you can see after the 20-30 minutes treatment, we use the 98% of the chemical pollutant. We also tested for the biological pollutant. So after the 10 minutes, we remove the most of the biological pollutant. So next slide, please. Next slide, please. So next part of the component is the gas reactors. So you can see the gas reactor, we using the packed bed reactor. So the reason why we choose the packed bed reactor is we can put some catalysis to dissociate the CO2 to the carbon monoxide and the oxygens. You can see from the diagram, we inject the CO2 from the bottom, and then there are the catalysts, and it helps to dissociate the CO2. The slide you see, that is the characteristics of the plasma reactor we have for the CO2. So currently, we have the prototype, but the limitation is, you can see the power intensity is relatively low. So we are trying to improve is the power intensity. So currently, we have the power intensity of the 0.3 watt. So we are aiming to increase that is the level of the 2 to 3 watt. The next slide, please. So this is the major system requirement. So basically, we aim to make the system can treat up to 300 milliliter per hour, which is suitable for the missions with the 3 astronauts to maintain their life. Also, we aim to generate the oxygen up to 10 gram per hour. So that is the limited by the airflow rate, the CO2 intake rate from the Martian atmosphere. So we are expecting the system power is about the 300 watt. So actually the power requirement from the plasma reactor is less than the 20 watt. And the system we expecting that is approximately the 20 kilogram, so which is relatively light compared to the existing concept of the in-situ resource utilization system. So we aim to make the system still longer than the 6 months, so which is suitable to perform the future crewed missions. So bottom picture shows the summary of our system now. So the middle is the test of the water system, and the third one is the assembled gas system. So currently, the TRL of our water part is the TRL 4, and the CO2 dissociation part is approximately the TRL 3. So we are expecting we advance this one by the TRL 5 by end of the 2024. So thank you, everyone. If you have any question, please feel free to let me know.
Thank you, Minkwan. Unfortunately, I think our next speaker is not available. It's not, so we are going to open a round of questions for our first 3 speakers. So if you have any questions here in the room, please just go to the microphone that is in the middle of the room to ask a question. And also, if you have any questions online, just feel free of putting it there. In the meantime, I have actually a question. I have several questions, but the first question, maybe it's because it's the most recent talk, is for Minkwan. So my question is, like, you set up a series of mission requirements for mission system requirements, and I think that you put you take assumption of 3 people. Are you considering how these requirements will escalate in the moment that we have more people or even less people? Are you considering that right now?
Yeah. So basically, we assume the 3 people. We assume the region is the one we need for the mission controller, 1 people we need for basically the doctors, and 1 people for the captain. So the requirement can be easily scaled based on the number of the people we need. For example, if we need 1 more people, probably we need extra 4 liters per day. If we need 1 less people, we don't need the 4 liters per day. So it is easily scalable.
Okay, thank you. Thank you for your explanation. I have another question. This is for Arturo. You have, yeah. Okay, so my question is about the samples that you use. It's like I saw that you use 2 simulants type, and it's like, what is the process to decide what type of simulant or what type of sample you are going to use for your experiments?
Yeah. Okay. See? Okay. Can you hear me? No.
This one?
please, super. Okay, that's better. We decided to use these two kind of simulants because in the scientific in the papers, they are cited, and they are the most reliable simulants so far. And there are many papers that support the use of this simulant for Mars application. So basically, that's why we choose. And this is the available in the market, to say.
Okay, thank you. So we have more questions coming in. So we have another question for you, for Arturo. So it's like, do you expect catalyst poisoning by sulfur compounds? If sulfur is a concern, could it be removed?
Yes, the sulfur, what we saw so far, that's the reason we heated up one of the simulants, the MGS1, because they possess magnesium sulfate, and we observed that we transform to magnesium oxide, we increase dramatically the catalytic activity. Also, we observe, it's not the experiments specified here in this presentation, but I try to impregnate nickel because nickel is the most common catalyst for Saboteur reaction. And when you support in this regolith, so it doesn't work. So it doesn't produce any methane and is contaminated. We think that is contaminated by the iron and also by the sulfate that we can find this in the simulant in the MGS1.
Okay, thank you. We have another question for Minkwan. It's like, with what kinds of contaminants plasma microbubble filter work best with?
So we tested for the two types of the contaminant, biological and the chemical. So for the biological contaminant, we verified it works for the all type of the biological pollutant, including the pathogens, virus, the spores. So for the chemical, we test for the couple of the chemical contaminant, such as the antibiotics or the very stable chemicals such as the DMMP. So the antibiotics, we saw the 60 to 70 of the reductions, but other very stable chemicals, we saw the very few reductions, such as the 5 to 10%.
Okay. Yeah, we have another question for you, Minkwan. Could you use other gases than air, for example, Martian atmosphere, for the plasma bubble purification system?
Yeah, so the system will need is just the oxygen to purify the water. So idea is that we using the CO2 first, and dissociate the CO2 to the carbon monoxide and the oxygens. Later, we're using this oxygen to ignite again the plasma to inject to the bubble.
Thank you. We have a question for Pia. How are you getting the limnospira you need for your 3D printing process?
Within the Melissa concept, there's a compartment with spirulina, and there's a possibility to harvesting the biomass. So we are still evaluating the exact process, but there are possibilities to harvest the biomass and use them for 3D printing and adding it to the plasticizer.
Thank you. So there are more questions coming in, but I'm afraid we have to continue with the session because there are more speakers coming in. So I kindly ask all of you that you check the questions online and you answer to all of them when you have some time. Thank you very much for our speakers, and we are going to move on with our next part of the session. One second, I need to find the proper lineup because I have everything mixed up. So I think, can you put the next presentation so I put my things on order as well? Yes, perfect. Our next speaker is James Cole. He's talking about the water extraction from Icy Lunar Simulants using low-power microwave heating. welcome. Yes.
Hello everyone. So my name is James Cole. I'm a final year PhD student at the Open University in the United Kingdom. So for a number of years, the Open University has been looking into using microwave heating as a possible ISRU technique. Mine specifically looks at using microwave heating to extract water ice from lunar simulants. So as we all know by now, there's growing evidence that the lunar poles contains vast amounts of water ice, and we could use that to sustain a human presence on the lunar surface and create a cislunar economy through the use of rocket propellant. We also know that microwave heating can heat up lunar simulants very effectively, getting to the melting point very, very quickly. However, water ice, especially at cryogenic conditions, does not couple to microwaves very well due to its poor dielectric properties. And so my research is really looking into how does the effect of water ice on lunar simulants affect the overall heating profile and therefore its use as a possible water extraction tool. So I performed a series of experiments where I took both Mare and Highland simulants, so LMS and LHS, and I added water contents from 3 weight percent to their respective saturation points, and then cooled them down to 100 Kelvin using a sample cooler. So this is the classic mud pie method, which gives you good replicability of your samples. I then placed them in our bespoke microwave heating unit, and I heated them up for 25 minutes using 250 watt microwaves in a vacuum conditions. So I'm looking at using 250 watts as I'm trying to use an amount of power that could be replicated by a rover or landing system in the next few years, so not trying to go for high power. The results you can see on the right. So you've got the Mare simulants in blue and the red simulants in, the Highland simulants in red. The water content of the samples goes along the right, and then up is the amount of water extracted. So the first thing to notice is that the trend between both the Highland and Mare simulant is roughly the same. So what this suggests is really that the difference in composition between the simulants doesn't have too much of an effect on the extraction. There's a slight difference, but that's more likely due to the microwave settings. But the more interesting point is that, firstly, as you increase the water content, you initially extract more water. That's fairly obvious. But the most interesting part is that when you get to near the saturation point, your water extraction drops. The reason why this happens is that your pore space between the simulant grains is filled with water, and so when it expands under freezing, it pushes the grains apart. The simulant grains are the part of the system that actually couples to the microwave and heats up. So if the grains have been pushed apart, you've got less contact area and you get less heat transfer. So overall, your extraction drops. What this means in the long run is that your microwave heating may be best served as a low to medium ice deposit extraction technique and not be used for sort of aiming for these very high deposits because it may not be as effective there. This work is explained in greater detail in my paper that is actually out of date because it's not in review. It was accepted 2 days ago, so that's some good news. So yeah, that's available in Astronautica soon. So I wanted to explore this phenomenon in greater detail and see, can we overcome this saturation point problem with more heating or higher powers, various things. And the easiest way I could think of doing this was to build an instrument that can measure the mass of a sample live while in the microwave environment. Firstly, this is extremely difficult because you can't have any metal. Microwaves will be absorbed by the metal and that will affect your results. So what I've used is a load cell system that is separated from your microwave cavity through the use of a small gap that the microwave can't permeate through, and therefore your load cell can measure the mass accurately. So the result on the right is just a crucible full of pure water, liquid water, just to prove that the system worked. We heated it with microwaves, and we were able to measure the difference in mass down to about 0.1 of a gram, so that's what the resolution is. So I'm hoping that we will use these for future experiments. We can get a greater idea of how the extraction changes with time. And there we go. I am just going to quickly present the work of my supervisor, Sung-Woo Lim, who unfortunately couldn't be here today. Now, I think as Jerry says, this is a eye chart, but essentially we've steadily improved the microwave heating unit, which is on the bottom left, which is what I use for my work. We've now added a gas processing system so we can capture volatiles such as water, so it's useful for my work. And then we've also continued the progression of the microwave heating payload, which will hopefully go to the moon one day. So we've now increased the TRL to 3 to 4. We've gathered the subsystems and acquired a 250-watt microwave generator through the help of Viper RF. And then we've also moved to TRL2 with a 3D printing gantry that will hopefully attach to the bottom of this payload and can prove that you can go through the sintering process and still use the product for 3D printing, and that is through work with AVS. So thank you for listening. I'm happy to take any questions about the water ice work, and I have colleagues in the crowd who can help with the sintering work. Thank you.
Thank you very much, James. Our next speakers are Dorian and Fardin Ghaffari, and it's going to talk about an important topic that is energy requirements for the systems. Welcome.
Hello, everyone. Thank you. Thank you to the organizers also for the opportunity to present our research today. So we'll be presenting an energy model for oxygen production on the moon. And we recently submitted this for publication in a journal, so we'd just like to highlight some of the key findings here. Before jumping into the results, I want to highlight the motivation and background. So I think everyone in the community here knows well that we perceive there to be a high value for lunar-sourced oxygen. And at the same time, there are multiple technologies for producing oxygen on the moon. In the ISRU world, we often hear the question of which of these technologies is best, and that really brings us to a fundamental question of how can we actually compare these different technologies. This is a particularly challenging question because each of those core technologies that you see in the graph there have quite different upstream and downstream processes. So the production chain is quite different. So in order to compare them, we need end-to-end models, and we need models where the feedstock composition is one of the key input variables into the model. Now, once we have those models, we'd like to evaluate them for different figures of merit. That could be mass payback ratios, reliability, profitability, but one of the key variables that we're going to need to assess is the energy requirements, so the kilowatt hours per kilogram oxygen produced. And so in order to tackle this fairly large question, we started off by looking at one of the simplest processes, which is hydrogen reduction, and that's also one that has some of the most available data. So now jumping into how we actually performed the analysis. We started off by looking at the process flow diagram. So you can see here that there are 7 steps between the raw regolith input to the liquid oxygen output. We used a combination of empirical data and first principles calculations to calculate the mass flow across this production chain. Once we calculated the mass flow, we know how much oxygen can be produced per unit input. And we looked at the energy requirements for each process unit. We summed up the energy requirements, and we divided by the oxygen output, and that gives us our result of kilowatt hours per kilogram oxygen. We then repeated this calculation by varying all the parameters in the model, so we did a sensitivity analysis. And very importantly, we also varied our feedstock composition. So we looked at a range of ilmenite concentration from 1% to 15%. And I'll now hand it off to Fardin, who's going to walk us through those results. Here you go.
So thanks, Dorian, and hello from my side. I'll start off with explaining the figure on the left, where we plotted the energy requirements over the ilmenite concentration. And you can see that the energy requirements strongly decrease with higher ilmenite concentrations, and especially the hydrogen reduction in dark blue, this step decreases strongly. That is because the energy needed, or we need to waste, we're wasting less energy on heating up non-reactive regolith material for higher ilmenite concentrations. And in panel B, we set the ilmenite concentration to 10% to better visually compare the relative energy consumption. And there we showed that hydrogen reduction is the highest energy consumer in the production chain, followed by electrolysis and liquefaction. And because of that, we looked at the hydrogen reduction step more closely on the top right, where we tried to find out which sub-processes are driving the high energy demand. And there we can see that regolith heating takes up the most energy, followed by hydrogen heating and insulation heat loss. And because of the high energy consumption of regolith heating, we identified that the enrichment factor in the beneficiation process is the most critical parameter in this production chain, because it strongly influences the ilmenite concentration inside our reactor. So because we have this function of energy depending on ilmenite concentration, and we know the ilmenite concentration across the lunar surface in certain regions, we can combine this data to map the energy requirements onto the lunar surface, which gives us this energy map with blue locations having low energy requirements for oxygen production via hydrogen reduction, and the red areas having higher energy requirements for this process. And this map highlights the importance of the lunar equatorial regions, and especially the lunar mare regions, which have the highest ilmenite concentration and thus the lowest energy requirements. And with that, I want to say thank you to the co-authors and to the research supporters, which were Spaceship EAC, ESA, Connectomix, and Space Radar. And thank you for your attention.
Thank you, thank you. Our next speaker is Farzaneh Gholami from Gradel, that she's going to talk about robotic additive manufacturing implementation, and hopefully she's going to tell us what is this thing that is here as well. Welcome.
Thank you. My name is Farzaneh Gholami, and on behalf of my colleagues at Gradel, I would like to present to you Gradel robotic additive manufacturing GRAM implementation in space manufacturing process technology. During the past days, we discussed a lot about our permanent presence into the moon and how to realize the lunar base. But as a matter of fact, sending each kilogram of materials into the moon would cost between 1 to 2 million. And so the question is that how we are going to realize this plan using, in a cost-efficient manner and yet or sustainable manner. And in Gradel, we believe that our technology can bring a solution to at least part of this puzzle with our unique GRAM technology. So if you look into the supply chain on the moon, so it starts with inspections of the raw materials and up to transportation of these materials to the material production base, which transforms these raw materials into usable resources that can be used for manufacturing the targeted parts. And the trick in between is to find the way to connect all these technology breaks. And we have managed to find these links between this raw material production and material utilization. So I will tell you how. Our raw material consists of fiber, 60%, and 40% resin. And realizing the fiber production on the moon has already been proved by Aachen University in the project Moon Fiber, which they have managed to produce fibers out of lunar regolith. And they have tested it already on low gravity and zero gravity tests. So we can be sure that it's feasible process. And in terms of the resin, we have the collaboration with Luxembourg Institute of Science and Technology to develop biosource resins or binders that they can be recycled, reshaped, and it means that after using the materials, the resin can be separated from the fiber, and both fiber and resin can be reused for multiple times. The technology itself has lots of advantages from material and energy efficiency and cost efficiency, fully autonomously, and sustainability. So if we go through the mentioned advantages, the material efficiency comes from the extremely optimized design. So that means that we get a part, we do the topology optimization to see where are the load cases, and based on that, and also the environment which the part would work, and with this, we program the robotic fiber winding path. And in the fully digital process, we can manage to manufacture the parts. And as an example, I can show you a part which has less than 200 grams, and it can take more than 9,000 kilogram tensile loads. This is the potential of technology, and that can be the same for any other design. And with this bionic design, we have managed to reach to up to 70% wave saving without jeopardizing mechanical functionality. The energy efficiency can be seen through all the process chain. So in the manufacturing phase, is energy efficient as it's possible to manufacture very complicated 3D parts, also very huge parts if necessary, using the fiber winding technology. So it's not the energy intensive process, and it's simple. And in case the part is used for mobile structures, it can also lead to low energy consumption during mobility phase. And at the end of life, as you saw, the fiber and resin can be used for multiple times, so it can avoid the energy consumption for the launch and also for remelting the regolith for producing the fibers. And to have a sensation of the sustainability, we need to have a more holistic overview into the whole supply chain. So from launch phase on to material production up to the utilization, manufacturing, and the use phase. So if we look into the whole process from beginning into the end, and to the end of life, which is not really the end of the life, because we are able to use the material multiple times. So you can see that the process, the technology, GRAM technology, is sustainable from economical, technical, and environmental point of view. And these are some of the applications that can be seen for thermal and radioactive insulators up to large structures and architectural parts for lunar habitats, spare parts, also the structures for rovers and mobile parts. So as an example, I can show you the part which is more for have been manufactured as a showcase. That you can see it's a huge part, but it can yet be carried out by one hand. So that's the potential application. The other application is the rover, which we have developed one in collaboration with 4 Point, as Ezrik suggested us to join our forces together. And you can see on the scene, and you can imagine any other applications. So reach us to us, and we can guarantee you less grams with gram. Thank you.
Thank you. I think our next speaker is online, Michele Hollist. Are you there, Michele? Yeah.
Yes, I'm here.
Yeah, we can see you and hear you clearly. So Michele is from OxEon Energy and is going to talk about MOXIE. Welcome.
Thank you. I'm pleased to have the opportunity to talk about the work that OxEon Energy is doing in the ISRU field. We're located in Salt Lake City and have over 30 years of experience in the electrolysis field. Next slide. But what this group would like to hear about is obviously ISRU, and OxEon was a part of the team that built the Mars Oxygen ISRU experiment, or MOXIE, which was a system delivered to NASA to produce high energy or high purity oxygen by electrolyzing the carbon dioxide in the Martian atmosphere. The MOXIE system was one of 7 science instruments included on the Mars 2020 Perseverance rover. 2 years ago yesterday, MOXIE achieved the first demonstration of fuel production by electrolysis on another world. Since then, MOXIE has operated throughout the seasons at multiple locations and at each time of day for a total of 14 oxygen production runs on Mars. That 14th run was actually just run yesterday on the 2-year anniversary of its first run. MOXIE has exceeded expectations in nearly every metric and has made ISRU a reality. Next slide. Since we developed the solid oxide electrolysis stacks, or which we also call SOXU for short, for the MOXIE program in 2017, the OxEon team has made significant advancements in both the scale and capabilities of this technology. Our newer variants of the solid oxide device have a 5-fold increase in the cell area and a 6.5-fold increase in cells per stack for a stack that is scaled 33 times the scale of the device that was demonstrated in the MOXIE system. This newer version, which is shown side by side with the MOXIE stack in the image on the slide, is what we refer to as a mission scale unit size. We estimate that it would require 6 of these OxEon mission scale SOXI stacks to produce 30 tons of propellant oxygen that would be used to fuel a Mars ascent vehicle, or a MAV, in the 19-month window between landing an unfueled MAV pre-supply mission and the next launch opportunity for a crewed Mars mission. This would meet the mission targets for a return. Each mission-sized stack would be capable of producing about 675 grams per hour of oxygen. Next slide, please. NASA has funded 2 separate programs to incorporate OxEon's mission-scale SOXI devices into demonstration systems for both lunar and Martian applications. For the lunar ISRU program, a breadboard system which included OxEon's mission-scale SOXI technology was coupled with a thermally integrated balance of plant to demonstrate the production of propellant hydrogen and oxygen from lunar ice located in the PSR regions of the moon. This program was done in partnership with the Colorado School of Mines and ultimately produced a breadboard system, which is shown in the slide images, that was capable of generating steam from a cold water intake to operate a high temperature SOXI stack and ultimately produce hydrogen and oxygen. The system was tested in the cryovacuum chamber at the Colorado School of Mines to demonstrate operation in a relevant environment. The lunar ISRU system demonstrated 2.8 kilograms per day of hydrogen and 22.4 kilograms per day of oxygen production, with an oxygen purity greater than 99.9%. Additionally, the capability of using the SOXI device to electrochemically compress the oxygen that was produced by the system to produce it at higher temperatures was demonstrated. The tight thermal integration of the SOXI stack with the balance of plant also allowed us to demonstrate a system-specific power for the entire unit below 50 kilowatt hours per kilogram of hydrogen produced during that relevant condition testing. The data that we collected during our demonstration testing was used to inform a techno-economic analysis of the system and inform pathways to the potential scale-up for a full-scale system. This analysis was conducted by Professor George Sowers of the Colorado School of Mines and was based on his lunar ice processing work that's been previously published. The results from this analysis indicated that this system is an economically viable path for commercial lunar propellant production. Next slide, please. OxEon's Martian ISRU demonstration system builds on the success of the MOXIE system and pairs electrolysis of Martian atmospheric CO2 with the electrolysis of Mars water. Both can be electrolyzed simultaneously in the same device to produce synthesis gas and high purity oxygen. In this Martian demonstration system shown on the slide, the mission scale SOXI stack is paired with a methanation reactor, which is able to produce methane from the stack generated synthesis gas. The breadboard system was tested at relevant pressure conditions in the Mars chamber at the NASA's Jet Propulsion Laboratory. It is capable of producing 675 grams per hour of high-purity oxygen and 167 grams per hour of methane. This unit would be the design basis for a 30-ton to a 300-ton Mars ISRU system. I would like to thank this group for their time and encourage anyone interested in further discussion to reach out to me at Michele@oxeonenergy.com or to view our website at oxeonenergy.com. Thank you.
Thank you, Michele. Please stay online for the questions. So we open now the floor for questions. Don't be shy. There is a microphone there. You can just go there and ask a question. In the meantime, we have already questions for our presenters. So the first question is for James. James, beside the mud-pie icy regolith approach, will you look into the shaped ice and/or water vapor freezing approach discussed on a previous day in your microwave heating evaluation?
I would like to. Whether I've got time within my PhD to do so, I will have to remain to see, but it's definitely something to think about because the mud-pie method, while it's useful for replicating samples quite efficiently, it's probably not the most replicable of lunar conditions, so something which is more frost-like will be more representative of what we're looking for, so something we can do in a future work, I think, is the idea at the moment.
Okay, thank you. We have two questions together for Dorian and Fardin. Do you plan to consider, one, that thermal energy might be cheaper than electrical energy, for example, if provided by concentrated solar, and two, that the waste regolith is hot and therefore could be used as heat source for other use, for example, keeping systems warm during lunar night?
I think I'll take the first question. So we tried to be agnostic to the energy source. So we just looked at how much energy the processes take, that is thermal energy and electrical energy. And there's this debate whether on the moon we're going for solar energy or photovoltaics or nuclear or solar thermal energy. And especially the hydrogen reduction reactor can definitely run on solar thermal energy. So we tried to be agnostic to the energy source and just looked at how much energy the different processes are consuming, and that's thermal and electrical energy.
Yeah, quick note. So I think there's a lot of opportunities for optimization of these systems when you consider the integrated system as a whole. We didn't consider heat exchanges that much, except for the fact that we have a lot of hot hydrogen that actually needs to be cooled down on its way to condensate water before the water is electrolyzed. However, when we consider a more full-scale model, we would want to look at all the opportunities to use the hot regolith to heat cold regolith, and I think it's also an idea that we need to look at potential drop-in technologies that can replace some of the modules that we have currently. So, for example, right now, as I mentioned, we used condensation of the water that comes out of the reactor, followed by electrolysis of liquid water. However, we could consider electrolysis of gaseous water. That would avoid needing to cool down the hydrogen and then heat it up again. So there's a lot of considerations, for the next steps in the model to consider all these improvements. Yeah.
Thank you. We have another question. This is for Farzaneh. It's like, do you have any indications on how resilient the resin plus regolith fiber composite is against vacuum and extreme temperature conditions, for example, the lunar environment?
Yes, and we are actually in the process for space qualification of the parts. So we have started this process under supervision of European Space Agency and Luxembourg Space Agency, which I would like to thank them also for their support. And when we started the GRAM technology, because of Gradel background in the space sector, we directly started with qualification of the process for space. And we have done till far some tests for thermal resilience, and yet we are on the final phases for space qualification of the process.
Okay, thank you. We have another question for you that just came in. It's like, how are the fibers cured during winding?
Yeah, the process is called wet winding, which makes it a unique process, as we have developed and patented the robotic head. And that means that we can get any kind of fiber as input, and adding the resin into the fiber occur on the robotic head. And it's on real time, and after that it can be winded directly. But the curing process, we can do it after a winding process. And yet we are on the research phase to see how it's possible to use, let's say, solar radiation as a method for curing, or other methods that are less energy intensive for curing.
Okay, thank you. So there are still more questions coming in. Unfortunately, we are running out of time. But before we finish this session, I would like to invite to the stage Philippe Reis. It has an important announcement to do.
Very important announcement. So just a very brief advertisement, perhaps. Just waiting for the slide to come up. On behalf of my dear co-editors, we're currently offering a special issue in Frontiers in Space Technology on the technologies for prospecting, extraction and utilization of space resources. So we are inviting you, the community, to submit technical papers to that special issue. We're still accepting submissions until the end of July. You can also submit your interest on the webpage here. So go to Frontiers in Space Technology, and you'll find this special issue on the front page. So we're accepting technical papers, as I said, on excavation, mobility, robotics, extraction techniques, dust mitigation, cryo storage, whatever topics related to ISRU technologies that we've heard about today. Okay, thank you.
Thank you, Philip. And I want to thanks again to all the speakers today. Just remember that there are still questions coming in that they are really interesting, so I invite you to check on them, answer if you can, and the rest for the same of all of you. So thank you, and I hope that you enjoy the end of this event.